Whether it is x plus y or y plus x, that doesn't make any changes. That is what about this commutative law. We are just going to remove the brackets and I am going to use those variables in order to regroup it. So that will going to be possible with the help of this associative law. If it is x plus y, then it is OR gate. So if it is inverted, it is NOR gate. So NOR gate is equal to inverted variable of x bar and y bar. Hello everybody, a warm welcome to one and all. Welcome back to this session 3 on chapter 2, that is Boolean Algebra. I am Rohini TS, lecturer, Department of Computer Science, Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. In the previous session of this chapter, we had a discussion regarding Boolean postulates and also have discussed regarding what do you mean by principle of duality theorem. So here we are going to convert the plus into product and product will be converted into plus, 0 will be converted to 1 and 1 will be converted to 0. So that is what principle of duality theorem, and also we had discussed regarding some of the Boolean theorems. So that includes properties of 0 and 1 and also have discussed regarding the idempotence law, then complementary law, then we had a discussion regarding this involution law. So now today's session we are going to have a discussion regarding this commutative law and then associative law. Along with that we will going to learn about this distributive law, then absorption law, and most important things is regarding this De Morgan's theorem. So we'll see what are the types of De Morgan's theorem we have and what are the applications of having this De Morgan's theorem. Everything that I'm going to discuss in my today's session. Let me get into the session that is regarding commutative law. So what this commutative law states that, so this law states that the order in which two variables are odd or ANDed make no difference. So whether it is x plus y or y plus x, that doesn't make any changes. That is what about this commutative law. So that means the order in which two variables will going to be odd, that means x plus y, or ANDed, that is x dot y is also equal to y dot x. So that is what we are going to have in the commutative law. So we'll see with the proof here, x plus y is equal to y plus x. So let me consider the value of y as 0 here. Let me consider this LHS part x plus y. So in the place of y, let me replace this y by 0. So x plus 0. So if I add any number with 0, I am going to get that number. So that it will be x. Then we have RHS here, that is y plus x. So in the place of y, let me consider the value as 0, 0 plus x. So if I add any number with 0, I am going to get that number. That number can be either 0 or 1. So here the resultant will be x. That means we have proved that LHS is also equal to RHS. So in the same way, let me consider the y value as y instead of 0 now. So now x plus y, let me consider the LHS value, that is x plus y. So in the place of x, let me consider x as it is, and in the place of y, let me consider the value as 1. So if I add any number or if I add any value either 0 or 1 with 1, then I am going to get the resultant as 1. Then let me consider this RHS, y plus x. In the y place, I am going to take 1 plus x. If I add any number with 1, the resultant will be 1 itself. That means LHS is equal to RHS. That is what commutative law. So here you can see the truth table. Here we have x and y. So you can observe the resultant of this x plus y and y plus x. So both the resultant will going to yield the same result. That's what we can say that this we have proved this commutative law. Same thing will going to be applied when we are going to do this ANDed operation. So now we are done with this odd operation. Let me see the things which is related to ANDed. So that is x dot y is equal to y dot x. So both will going doesn't make any difference here. So there is no difference when we are going to change the order of that variable along with either it is ordered or ANDed, then it will going to yield the same result. So that we can see here, let me consider the y value as 0. In the place of y, I am going to consider that as 0, x into 0. So now we'll see how this will going to work well with this ANDed operation. That is what x dot y is equal to y dot x. Let me consider the value of y as 0 here. X dot 0, that is x dot y. So whatever could be the value, if I multiply any variable with 0, at last it will going to yield the resultant as 0 itself. Let me consider the RHS now, y dot x. So in the place of y, I will take 0 into x. So that it can be either 0 or it can be 1. So if I multiply 0 with any other number, it will be 0. That we have proved that LHS is equal to RHS. We'll see the next one. That is when I am going to consider the y value as 1. So let me consider the LHS, that is x dot y. So x dot 1. So if I multiply any variable with 1, at last we are going to get the resultant as 1 itself. Let me consider RHS y dot x. In the place of y, take it 1 and dot into x. If I multiply any variable with 1, at last again it will be 1. That means we have proved LHS is equal to RHS. So here you can see the truth table of this x dot y and y dot x. Both will going to give the same resultant. That means we can say that commutative law has been proved. We'll see the next one, that is related to associative law. So this law allows the removal of brackets from an expression and regrouping of the variables. So in the associative law, we are just going to remove the brackets and I am going to use those variables in order to regroup it. So that will going to be possible with the help of this associative law. So that x dot into y dot z can be written as what? X dot y into z. We'll see how this will going to give a resultant with a proof. Let me consider the y value as 0 here. X dot y into z. In the place of y, take the value as 0, x dot into 0 dot z. If I multiply any value with 0, it will be 0. So that 0 into z will be 0, x dot 0. If I multiply any variable with 0, again it will be 0. So now we have done with this LHS. Let me consider the RHS now, that is this one, x dot y into z. So x dot 0 into z. So x dot 0 will going to give you the 0, 0 dot z will be 0 itself. That means we have proved LHS is equal to RHS. Let me consider the y value as 1 now. So x dot y dot z. So x into y dot z here. In the place of y, consider y value as 1 now. If I multiply any value with 1, then I am going to get that variable or a value. For example, if that z is 0, then if I multiply 1 with 0, it will be 0. So that this z will going to be produced here. So that any value which is multiplied with other variable, we are going to get the variable value. So that x dot z. So it can be written like this. We'll see the RHS here, that is x dot y into z. In the place of y, take the value as 1, x dot 1. If I multiply any variable with 1, then it will be that variable. So consider this as x dot z. So it can be written like this. That means we have proved LHS is equal to RHS. Same thing that you can be see here in the truth table. So both will going to yield the same resultant. That means we can say that we are done with this associative law. We have proved by removing of a brackets of that particular expression can be regrouped of the variable. Regrouping of variable can be done by removing the brackets, but both will going to yield the same result. That is associative law. So x plus of y plus z will going to be equal to x plus y into plus z. So let me consider the y value as 0 now. Let me take the LHS, that is left hand side, x plus of y plus z. In the place of y, put 0. Then if I add any number with 0, then I am going to get the resultant as a variable. So here I am adding 0 with z, the resultant will be z itself. That means x plus z. So if I add x plus z, it will be x plus z itself. Let me consider this RHS now, x plus y into plus z. In the place of y, put 0, x plus 0. If I add any variable with 0, again I am going to get the same variable x plus z. So it will be x plus z as a resultant. So that we have proved LHS is equal to RHS. So now let me consider the y value as 1 now. So x plus of y plus z. Consider 1 plus z. If I add any number with 1, then I am going to get the resultant as 1 itself. So that x plus 1 now. So x plus 1 in the sense 1. If I add any number with another variable, then the resultant will be 1 itself. Consider the RHS x plus y of plus z here. So that in the place of y put 1, x plus 1. Again, if I add any number with 1, if I add any variable with 1, the resultant will be 1 itself. So 1 plus z. So if I add any variable with 1, again it will be 1. So that LHS is equal to RHS. Same thing can be seen in this truth table. So we have x, y, z, and we found out this x plus y plus z, and of x plus of y plus z, then x plus y of plus z. So these two columns are identical, so that we can say that we have proved this associative law by removing the brackets of the expression and regrouping of those variables. So now we'll see the theorem 7, that is distributive law. So what it states, this law allows the multiplying or factoring out an expression. We'll see how it will going to work. X dot into y plus z, it will be equal to xy plus xz. So how it will going to give this kind of resultant? We can see here x into y plus. So I am multiplying this one, I am multiplying this with 1. This one in between we have this plus operator. So we'll see this distributive law with a proof here. So that consider x value as 0, x into y plus z. In the place of x, consider the value as 0, 0 into y plus z. So if I multiply any value or a variable with 0, it will going to give the resultant as 0 itself. Next, we have a RHS here, that is xy plus xz. In the place of x, take 0. So, if you don't have any variables in between this x and y, that is understood that we have a product. So, that x dot y, so 0 dot y or 0 multiply y will be 0 plus 0 into z. It will be 0. So, 0 plus 0 will be 0. That means we have proved LHS is equal to RHS. And the same way, we'll take the x value as 1 now, x into y plus z. So, 1 into y plus z. If I multiply any variable with 1, we are going to get that variable. So, the resultant will be y plus z. So, xy plus xz. So, in the place of x, take 1, 1 into y plus 1 into z. If I multiply any variable with the 1, then it will be that variable value. So, it will be y plus z. We have proved LHS is equal to RHS. So, this is what we are going to get out of this distributive law. So, in the same thing, we can see one more theorem which is related to distributive law. X plus y into x plus z is equal to x plus yz. How we are going to get this? We'll see now. I need to multiply LHS in order to get this RHS now. X into x, that is what this one, and x into z, x into z plus x into y, then this one y into z. After this, as we all know that x into x will going to give you x. For example, 0 into 0 will be 0 and 1 into 1 will be 1. So, if I multiply the same variable with the same variable, then we are going to get that variable only. So, that x into x will be x here. So, otherwise remaining value will going to be written as it is. So, by using this absorption law, I am taking a common, so that x into 1 plus z. So, this is 1 plus z plus xy and yz will be as it is. After that, consider this as x and 1 plus z. So, as we all know that if I add any variable with 1, it will be 1 itself. So, that x dot 1. So, x dot 1 will be x as it is. Then, I am going to write the remaining value here. Again, I wanted to take a common in between this way expression. So, let me consider the value of x into 1 plus, I will cancel this one, then it will be 1 plus y yz will be as it is. After that, as we all know that 1 plus y will going to give you 1. If I add any variable with 1, it will be that 1 itself. So, that x into 1 will be x. Then, I am going to write the value x plus yz. That means we got the RHS here. So, we have proved LHS is equal to RHS. This is regarding this distributive law. Among these two expressions, we have same x in both the side. So, that let me consider the x as a common factor here. So, x of 1 plus y. So we are going to take this x as a common factor. So as we all know that if I add any value with 1, then we are going to get 1 itself. So that it will be x into 1. So if I multiply x with 1, then I am going to get x again. That means we have proved that LHS is equal to RHS. Next one, x into x plus y is equal to x. So here let me consider this LHS, that is x into x plus y. After that I will multiply this x with x and x with y. So that x into x will be x into x plus x into y will be xy. So after that, as we all know that if I multiply any variable with the same variable, then I am going to get the same variable as a resultant. For example, 1 into 1 will be 1 and 0 into 0 will be 0. So that x into x, in the place of x into x, I am going to take that value as x itself plus xy. Again, I can take a common factor out of this, x into 1 plus y. So that if I add any number with 1, then it will be 1 itself. So that x into 1 will going to be x. We'll see the next one, that is xy plus xy bar is equal to x. How we are going to get this? Consider the LHS part, that is xy plus xy bar. So consider this x as a common factor, x into y plus y bar. As we all know that if I add any variable with its complement, then it will going to give 1. So that x into 1. So in the place of y plus y bar, it is 1. So that x into 1. If I multiply x with 1, then we are going to get x as a resultant. In the same way, we are going to get the resultant for all these Boolean expressions. So that means we can reduce this complexity of this Boolean expression by giving or by taking or absorbing this common term. It's all about regarding this absorption law. So now we'll see the most important topic of this chapter, that is De Morgan's theorem. So here we have two theorems under this De Morgan's theorem. It has De Morgan's theorem 1 and we have second De Morgan's theorem. So we'll see the De Morgan's first theorem now. What it states, so when the or sum of two variable is inverted, this is same as inverting each variable individually and then adding these inverted variables. What it means? So that when the or sum, so that means I have two variables, consider x and y. So which operation we are using? Or sum. That means it will be plus in between those two variables is inverted. So it will going to be complemented. So this will going to be same as inverting each variable. Let me invert each variable x as well as y, each variable individually and then adding these inverted variable. Adding in the sense what? We have to use product. So x plus y bar is equal to x bar into y bar. That is what De Morgan's first theorem states that. So when two or sum of two variables is inverted, that will be same as inverting each individual variable and then adding these inverted variables. So it can be written as x plus y whole bar. So if it is x plus y, then it is OR gate. So if it is inverted, it is NOR gate. So NOR gate is equal to inverted variable of x bar and y bar. So that you can see here x plus y bar is equal to x bar into y bar. So you can see the truth table here. So we have x, y and we have x bar, y bar. 0 0 1 1 0 1 0 1. Inverted this x value, then x complement will be what? 1 1 0 0 here. Y complement 1 0 1 0. So now let me add x plus y. So x and y. 0 plus 0, it will be 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. So if I invert it, that means if I find the complement, 0 will be converted to 1, 1 will be converted to 0, 1 will be converted to 0, again 1 will be converted to 0. So after that I can have the multiplication of this x and y. So 1 into 1, 1. Then 1 into 0, 0. 0 into 1 will be 0. 0 into 0 will be 0. So what it indicates then, if you observe these two columns, that is x plus y bar and x bar into y bar, both will going to yield the same result. That is what we have proved in this De Morgan's first theorem. So you can compare the column of this x plus y bar and x bar dot y bar. Both these are identical. That means we have proved the De Morgan's first theorem. We'll see about this De Morgan's second theorem. So here what it states, when the AND product of the two variable is inverted. So AND product of two variable, AND in the sense product. AND product of the two variable is inverted. So I have inverted this variable product. So this is same as inverting each variable individually and ORing these inverted variables. So what it equal? So it will be equal to ORing each variable individually. So that this can be seen, or it can be written as how x dot y whole bar is equal to x bar plus y bar. So this is NAND gate that is equal to sum of two inverted individual variable here. So you can consider this truth table. We have x and y, we have x bar, y bar, and I have found out this x dot y. So that is 0 into 0 will be 0, 0 into 1, 0, 1 into 0, 0. So 1 into 1 will be 1. So now you can see the conversion, or you can see the complemented version of this x dot y, that is x dot y complemented. So 0 will become 1, this 0 will become 1, this 0 will become 1, this 1 will become 0. So that we can see the x plus y whole bar. So now we'll perform OR operation with this x bar and y bar. So x bar plus y bar. So already we know the value of x bar and y bar. Let me OR these two. 1 plus 1 is 1. 1 plus 0, 1. 0 plus 1 is 1. And 0 plus 0 will be 0. So if you observe these two columns, the resultant will be same or identical. So that we have proved this x dot y whole bar is equal to x bar plus y bar. So that means the De Morgan's second theorem is proved. So it is regarding De Morgan's first theorem, De Morgan's second theorem, and this is most important question. Either it can be asked for 3 marks or for 5 marks. So it is very important topic. Let me move to the applications of De Morgan's theorem. So where and all can we use this De Morgan's theorem? So it is used in simplification of Boolean expression. Till now we have done that. We can use this De Morgan's theorem in order to simplify the Boolean expression, and De Morgan's law commonly applied to text searching using Boolean operators like AND, OR, and NOT. So we can use this De Morgan's theorem in order to apply, or in order to get the text searching methodology, and it is also useful in the implementation of basic gates operation with alternative gates. So these are the 3 important De Morgan's applications that we can see. So, and this is also important even for 1 mark or for 3 marks. It's all about today's session. Let me meet you in the next session. Thank you.